Okay, so there's a big focus, okay, worldwide, but especially in North American society, on efficiency, trying to make things work better and use less energy to do the same job, okay? Certainly in my lifetime, but I mean, we're talking all the way back to the Stone Age when we talk about that, okay? There has been a lot of improvement in efficiency of very basic items, okay? One of the biggest ones, light bulbs. Okay, how many of you actually have a Thomas Edison tungsten filament style light bulb in your house? Yeah, I didn't think so. Okay, they're actually fairly hard to find anymore. Okay, but up until probably about 15 years ago, that's what you had. Okay, you bought a new house, or you went to the grocery store and you bought a replacement light bulb, and it was a Thomas Edison, like 200-year-old, okay, style tungsten filament light bulb. Those were 60 watts. That meant that they used 60 joules of energy every second. Okay, and they would make light. But they would also make what? Heat. Tungsten is a terrible conductor of electricity. So when the electrons would try and force their way through the tungsten filament, they would get slowed down and the filament would glow white hot, okay, emitting a lot of light. Right? If a tungsten filament light bulb burnt out, you had to wait quite a while before you could reach up and grab it to replace it. Okay? With a modern light bulb, you can reach up and right away, you unscrew it. Okay? It's not hot. Because LEDs that have replaced the Thomas Edison style light bulb, okay, now can emit the same amount of light using 4 watts of electricity. Because LEDs emit almost no heat. Okay? They just turn the electricity directly into light. They are far more efficient. Okay, guys, I can tell you that when I replaced all of the light bulbs in my house, from the tungsten filament ones to what we had after that, which was compact fluorescent, they were a little coiled, okay, they got away from those because they had mercury in them. Save the environment, you kill the environment, just one of the, yeah. So when I replaced those, my electricity bill was cut nearly in half because I went from a 60-watt light bulb to a 13-watt light bulb. Okay, it still made some heat, but it was way more efficient. Okay, now you go down to an LED, even more efficient than that. Okay, so the focus is obviously to be responsible with our resources. Why waste them? We can do something more efficiently. We want to do that. Another place where we see that is in cars. Okay, probably most of us still have at least one car in the garage that is a purely internal combustion engine vehicle. Okay, when people have a car that only runs on gas. That's usually the way it is, okay? How many people have a hybrid car in the garage? Okay, not so many, right? How many people have a purely electric car? Also, usually a pretty small number, okay? Nobody's driving one of those dumpsters? I mean, Cybertrucks. Sorry, they're so ugly. So I can't get past it. It's just so ugly. Okay, you'll never unsee that now, by the way. Every time you see a Cybertruck, now you're going to see a dumpster. That's what they look like. Okay, so obviously an internal combustion engine is trying to do something that is, by its very nature, inefficient. It is trying to turn heat into mechanical energy. Okay? We know that that's not efficient. We've learned that like on the first day of the unit. That's one of the least efficient things to do. Okay? So in your internal combustion engine car, okay, the gasoline is mixed with air, it's put into the combustion chamber, and the little spark plug at the top sparks. Okay? That ignites the air-fuel mixture, which then explodes, okay? And that explosion creates expanding gases because of the heat that pushes the piston down. Okay? That's what we call the power stroke part of the internal combustion engine. Okay? That's what drives your car forward. That reaction is so inefficient that your car has to use over 30% of the energy in its fuel to keep the car from destroying itself. So much heat is generated by that reaction, that chemical reaction of burning fuel, okay, that without a cooling system, your car would melt down. Okay? So in a typical gasoline-powered motor, this is where the energy goes. Okay, engine losses. Okay, this is things like the radiator. That's the thing that cools your car off. Okay, it runs coolant through the block. Okay, that absorbs the heat, and then it goes through this thing that's usually at the front of your car that has a big fan on it. Okay, and it's trying to blow the heat from the engine out into the surroundings so the engine doesn't die. Okay, so thermal energy such as radiator, exhaust heat. You ever notice the stuff coming out of the pipe is hot? Okay, that's again wasted energy. Okay, 58 to 62% of the energy in your fuel is there. Let me put that in real life terms that will make you sad. You put $100 of gas in your car. $58 to $62 of it is completely lost to the surroundings. You might as well just throw money into the air because that's what your engine is doing. Okay? It is throwing away $58 to $62 worth of its energy, okay, into the surroundings. Okay. Combustion losses. Combustion is not 100% efficient, about 3%. Pumping, so you got water pumps and things like that. Okay, 4%. Friction. Okay, what do you have to make sure your car always has in it to make sure it doesn't die? It's slippery stuff.
Lubricant?
Yes, we call it oil. Okay? You have to put oil, it's a lubricant, okay, into your car. Without it, there will be a lot of friction. The more friction there is, the more that heat number goes up and the less efficient your car becomes. Okay? If it's not sufficiently lubricated by oil, okay, that is obviously changed regularly, it will simply get too hot. The pistons will continue to expand, as all hot things do, and they will not be able to go up and down inside the cylinder, and the connecting rods will break. That's the things that connect it to the drive shaft. Okay? When they break, they typically go through the walls of the cylinder and destroy your engine, something called seizing. Okay? And that's bad. That requires you to get a new motor. Okay? It is all done after that. There's no rescuing that. Okay? All right, so you want to watch out for friction. Auxiliary electrical losses, so things like your climate control system, your fans and all of that kind of stuff. Okay, if you have heated seat here, heated steering wheel. Oh, was it Miss Sikora? Okay, just go down to her classroom. That's usually how things work. You just go to their classroom. Okay, so all that fancy stuff, you know, keeps your car comfortable inside, okay? Headlights, okay? Windshield wipers, rear window defroster, all that kind of stuff. Okay, another 0 to 2%. Parasitic losses, water, fuel, oil pumps, ignition systems, engine control systems, pollution control systems, okay, like a catalytic converter, things like that, 4 to 6%. So the remaining energy directed to your wheels that actually makes car go, okay, 16 to 25%. Okay? If you have a highly efficient smaller vehicle, it's probably closer to 25. If you drive a big truck like me, it's probably closer to 16. Okay? Because, well, mass works against you in that case. Okay? The more mass you have to move around, the less efficient you are going to be. The bigger the motor, the less efficient it's going to be. Okay? Does that make some sense? Okay, so how can we make that more efficient? Well, we've done pretty much everything we can to the internal combustion engine to make it more efficient. So what do we do instead? We add an electric motor to it. Okay? When does an internal combustion engine use the most fuel? In the city, like accelerating and decelerating, or traveling on the highway at a constant velocity? Accelerating and decelerating. When you guys get to the point where you're shopping around for a car, okay, you'll see that they rate the fuel economy of the car, city, highway, and then combined. There'll be 3 different numbers in liters per 100 kilometers. Okay, the city number for a purely internal combustion vehicle is always lower than the highway, because on the highway you're in the highest gear, okay, or lowest gear, whichever way you want to look at it. Okay, you're in 5th or 6th or 8th or 10th. All those cars have different transmissions. Okay, you're traveling along the highway at a constant velocity. It doesn't take very much force or very much energy to keep you going. Okay, but when you're trying to change your energy, accelerating and all of that, you use a lot more. Okay, so a hybrid vehicle puts an electric motor on board with a big battery to assist the internal combustion engine under load. Okay, so when you're traveling down the highway, are you using the electric motor very much? Almost not at all. Okay, the highway efficiency of a hybrid vehicle and the highway efficiency of a purely, like if you had exactly the same model, one hybrid, one not, their highway mileage would be about the same. Okay, the hybrid system only helps under load. That is when you are accelerating. That's when your engine is going to be least efficient. You can help it with an electric motor, then it doesn't have to work as hard. And sometimes you can put a smaller motor in. Okay, a smaller internal combustion motor in. All right, so in a hybrid vehicle, okay, the electric engine comes on when needed. Okay, so if you push the accelerator down to go, the electric engine kicks on and helps the car accelerate. Okay, so you can see the difference in here. For this is a hybrid vehicle, 65 to 69%, okay, versus 68 to 72% for your engine losses. You still have an internal combustion engine, so these things are all still present, but maybe it's a little smaller because you have a hybrid. Okay, parasitic losses, 4% to 6%, okay? Water, fuel, oil pumps, ignition system, engine control system, same thing, okay? The parasitic losses are about the same. Auxiliary electrical losses, also about the same, but you have a little more in a hybrid vehicle because you have a little more electrical in a hybrid, right? You got a big battery connected to a big electric motor or several electric motors. Okay, drivetrain losses, okay, are, you know, about the same, 3 to 5%. Okay, idle losses go way down. Because what does a hybrid vehicle do when you're idling? Turns off the internal combustion engine. Okay? In fact, most vehicles do that now. They have, when you pull up to a stoplight and you're just sitting there at a red light, the engine shuts off. Okay, and just runs on the battery. Why have the engine running if it's not going to do anything? I hate that. I've driven a few cars that have that thing on them, and it's just like you push the gas and then, ooh, you hear the starter kick on, and then the car goes. I find that really annoying because I'm old school. Okay, but hybrid vehicles, they turn the engine off. If you're just idling, the engine goes off. You run off the battery. Okay, because you have a much bigger battery. Okay, now energy to the wheels goes from 16 to 25 to 24 to 38. Okay, and the way you get that is you have this. That is something you do not have in an internal combustion engine. It is called regenerative braking. Remember when we talked about the thermocouple? Okay, way back on the first day? Okay, there are thermocouples in the brakes of hybrid vehicles. So when you squeeze the brakes and all that friction is slowing the car down and making all that heat gets turned back into electricity that goes back and charges the battery. So now instead of braking being a complete waste, like it is in an internal combustion engine, you get a little electricity back. Not a lot. Okay, like it's a game for me. We have a plug-in hybrid vehicle, okay, and whenever I drive it, it's a game. Because it has this little thing it calls the brake coach, and it tells me whether I'm doing a good job or not on my regenerative braking. If I like slam on the brakes and screech to a stop, I get like 5% on my braking. Okay, but if I slow down very slowly and just roll to a stop gently, I get 100%. Okay, and I'm usually somewhere between 90 and 100 if I don't have to like emergency really quickly brake. Right, so the slower I can do that, the more of that energy goes back into the battery. Okay, then the battery charges itself that way instead of charging from where? Where does the battery usually charge from in a hybrid? It uses the internal combustion engine to charge it. So when the engine is running, the alternator, which is this kind of circular shaped thing, it's about this big, okay, and it has a belt running to it. If you've ever been next to a car that's squealing, it's usually the belt that goes there that's squealing. Okay, that creates electricity. Okay, it's just a little generator that the belt turns it and generates electricity. Well, that goes back to charge the battery as well. Okay, so the car actually uses its own fuel to charge its own battery. Believe it or not, it's actually really efficient. Okay, so you have the regenerative braking and you have the charging of the vehicle from its internal combustion engine. If you have a plug-in hybrid, okay, it actually has two different electrical systems. It has the hybrid battery that works like this, and it has a purely drive me like an electric car battery. Okay, so it's two different ones. And the plug-in one only charges the drive me like an electric car battery. Okay. All right, everybody with me there? Okay, so that's more efficient. It's not helping you on the highway. If you just drive on the highway all the time, a hybrid vehicle is a waste of money. Okay, it's not going to save you any money in fuel. Okay, now, what if you switch to, whoop, where'd the electric one go? I lost the electric one. And now this is good. Now, I have it somewhere here. Where are the energy? There. Okay. Where's the electric? All right, so let's say you've got a Tesla or a cyber dumpster truck. Okay, so if you're driving that along, okay, you only get to charge that if you do what with it? You have to plug it in. Okay, you have to plug it in to charge it. Right? You do get a little regenerative braking with any electric vehicle, but that's not going to keep the car going. Okay, you have to plug it in order to get it charged up and ready to go. Why do we want to switch to electric? Why is electric so much better? Why is an electric car so much more efficient than an internal combustion engine?
I thought you were just talking the internal, I was going to say
Oh.
better for the environment.
Well, that's an it depends answer, actually. Better for the environment depends on where you get your electricity from. Okay, in Alberta, where do we get our electricity from? Oil, gas, and coal, primarily. Okay, everyone goes, well, what about the wind farms? Those wind farms down in Pincher Creek, even though they've doubled the number of turbines, still account for a single-digit percentage of our overall power grid. And we have zero hydroelectric or very little hydroelectric electricity in Alberta. Most of our electricity comes from burning fossil fuels. So you plug in your car, you're still burning fossil fuels to charge it. That said, it is more efficient. So your carbon footprint does go down by having an electric car. Okay? But what's in the batteries? Yeah, lithium, and if you've ever seen a lithium mine, okay, they make the oil sands in Fort McMurray look like a Greenpeace-sponsored hotel. Okay, like they are a big giant pit. Okay, they dig a big giant pit. Okay, and they harvest all of the lithium. So the environmental impact to build an electric car, you have to say to yourself, what am I buying this car for? Am I buying it to save myself some fuel? Am I buying it to save the world? You're going to save yourself fuel, but you may not save the world. Okay? You might do a little bit better job of saving the world, but you're not saving the world. You're not completely reducing your environmental impact. Plus, this hasn't come up yet, but those batteries don't last forever. Where do they go when we're done with them? I don't know. Yeah, somewhere, they got to go somewhere, and they're quite toxic, actually. So there's that. That part hasn't really been kind of brought up so much. So you got to do your research. A lot of people just bought an electric car because they thought, I'm the savior of the environment. And they're probably not as much as they think. Okay? But it is a lot more efficient. An electric engine is far more efficient than an internal combustion engine. Okay? So you use a fraction of the energy to do the same job. Okay? It's that much more efficient. Okay? We have a plug-in hybrid that we bought a couple of years ago. If I disable the electric motor, so that I'm just driving because I can just tell it I want to save the electric for later, okay, and just drive on gas, I can at best get around like 7.5 liters per 100 kilometers. If I'm enabling all of the systems, electrical, hybrid, all of that, it can drop below 3. Okay, like it literally uses nothing but the electric motor. Okay, now when I plug it in at home, yes, okay, my power bill goes up. But we did the calculation, it cost me $1.25 in electricity to charge the battery, which can take me 50 kilometers. That's way less than the amount of fuel, right? If I'm getting optimal fuel economy, okay, I am using 3.5 liters to go 100 kilometers. So 1.75 liters, okay, to go 50. In gas, current gas prices, that cost me close to $4. It only cost me $1.25 in electricity. Okay, it's more efficient, costs me less money. Okay, that's good. It was even better back when all the charging stations in Okotoks were free. Okay, because I used to hate that. I used to drive around and look at people plugged in and go, that's my tax dollars paying for your gas. I don't get free gas, and I get all mad. And then I'm like, don't hate the player, hate the game. And bought a plug-in hybrid, and I became part of that problem. Okay, and I'm like, yeah, I'm plugging in for free. Okay, you guys can all just deal with it. We actually got nasty notes on the car. Okay, people like wrote nasty notes and put them on the windshield. This is my taxes paying for your gas. I'm like, yeah, I used to think like you, but hey, don't hate the player, hate the game. Okay.
This piece of paper will stop them.
Yes. Yeah. Well, and they would unplug it. Like, yeah, it's.
Oh no, minor inconveniences.
Well, I was trying to get my fuel for free. That's not a minor inconvenience. Okay, okay, but now you have to pay for it. Anywhere you plug in Okotoks is no longer free, and you do have to pay for it. So, with an electric vehicle, okay, your accessory losses are still about the same. Okay, your electric drive system is only 18% loss. That was 60% in the internal combustion engine. So that's a significant savings. Okay, energy to the wheels, okay, anywhere from 87 to 91%. Okay, basically your losses are a little tiny bit of heat and wind resistance. Okay, unless you drive a cyber dumpster, which is like hyper aerodynamic because of its ugly shape. Okay. All right. Okay, everybody getting the idea here? All right, so here's what efficiency comes down to. Okay, efficiency comes down to this. It's a percentage. If this thing ever switches back. As soon as I go to write, there we go. Okay, so efficiency is a percentage. I calculate the efficiency of something by the same method you use to calculate the efficiency or the percentage you got on the test. You take what you got on the test and you divide it by what the test was out of. And then you get a decimal, right? So if you got 85, what decimal are you going to get? 0.85. Okay, so when you do efficiency calculations, you're taking the actual work done by the input energy you had to give it. Okay, so the actual work done divided by the total energy actually used to do that work, okay, gives you the percent efficiency. All right, if you got 4 out of 5 on a quiz, you went 4 divided by 5. You got your percentage. Okay. All right. Everybody okay with that? Okay, so is this a pretty easy formula to use? It's like V equals D over T, right? The trick here is deciding which number is which. All right. Okay, so that's what we were looking at. Oh, there was the electric one. It was further down. Okay, so let's look at a couple of examples here, if it ever switches back. All right, let's look at question number 1 here. Okay, this actually is in your workbook, so if you have that with you, this question is there. If not, write this question down real quick. So we have an internal combustion engine, and its efficiency is 15%. What does that look like as a decimal? 0.15. Okay, so I'm just going to write efficiency equals 0.15. Okay, that's an easy little one to do in your head. Okay. Is with an efficiency of 15% is used to do 3.2 times 10 to the 4 joules of useful work. Okay, so in our formula here we had efficiency equal useful work divided by the mechanical energy input. Okay, so that number there, the 3.2 times 10 to the 4, is that W or EI? It's W. It's the useful work actually done. All right, they want to know the mechanical energy input, EI, okay, that had to be supplied by the combustion of the fuel. Okay, do I have to manipulate that formula?
Yeah.
Can we do that pretty easily? Okay, what do I do with EI? Multiply it over to the other side. Okay, and then what do I do with efficiency? Divide it over to the other side. Okay, now, talk yourself through this. Ask yourself if it makes sense. If you divide a number by a decimal, does it get bigger?
Yes.
Yes. Okay, should this number be the bigger number? The one we're trying to calculate? Yeah. Okay. So, our initial energy input is going to be 32 or 3.2 times 10 to the 4 joules divided by 0.15, our efficiency. Okay, and that should give us 213,333.33 joules. Okay, is that a lot of energy? It is. At 15%, you need a lot. Okay. Question number 2 sometimes gives people trouble because it feels like it's not clear which number is which. Like which one is the input energy and which one is the work. If you're given in a question both the work and the input energy, the work will always be smaller. Nothing can be 100% efficient. If you ever do an efficiency calculation and get 1 point something, okay, you had them backwards. Nothing can be more than 100% efficient. Okay, that means the number on top, W, the useful work done, is always smaller than the input energy, okay, the bottom number. So in this one here, which one is the top number? The 1.96, yeah, okay? The useful work, okay, it says actually useful mechanical energy output, that's useful work, okay, is 1.96 times 10 to the 4, okay, joules. And then our energy input is the bigger number, 5.61 times 10 to the 4 joules, okay? This looks like it's probably a little bit more efficient than the car in the last question. All right, we're looking for the efficiency. Is this one probably the easiest mathematically?
Yep.
Once you sort out what's what, yes, it absolutely is, because you don't actually have to do any algebra. Okay, it's work over energy input. Okay, so our 1.96 times 10 to the 4 divided by 5.61 times 10 to the 4. Have you guys done exponent laws? Yeah, you have, because that's like grade 9, right? Okay. If they have the same exponent, do you need to include the exponents, or can you just divide the bases? You can just divide the bases. If you're not comfortable doing that, you can put the whole number in, okay? Just like you did with Avogadro's number, 1.96 E4, okay, divided by 5.61 E4, okay, and you get 0.3494, okay, percent, or 34.93%. Okay, so you know, my big concern with efficiency is that you know what it is. Okay, so if I gave you a multiple choice question, you'd be able to know that I was talking about efficiency. Okay, and I have one simple efficiency calculation on the test. Okay, it's in the multiple choice. It's not even in the written. Okay, it's that simple. All right, I would like you guys to try 3, 4, and 5, please. Okay, give you a little bit of time on them. Big thing with efficiency is kind of like, this is one of the things in physics, is kind of like biology. Okay, be able to know when it applies. Okay, I give you a situation, okay, and you think it's about how well energy is being used or how well work is being done, then it's an efficiency question. Okay, and then obviously a simple calculation. How will you know if it's an efficiency question? It'll definitely have the word efficiency in it. Okay, like if it's a problem-solving question, it's definitely going to have the word efficiency in it. They're either going to give you the efficiency as one of the givens, or they're going to ask you to calculate it. Okay, either way, it'll have the word efficiency in it. There really aren't any other questions where you would get input, energy, and work, okay, as givens other than this. All right, so something to be aware of for your exam tomorrow. Now, as always, you may begin your exam early. So if you can be here by 10 after 8, you can start at 10 after 8. Okay, I have no problem letting you start early, okay, if you want a little bit of extra time. Okay, you will be allowed to have your, I can't remember if I put the formulas on the front of the test. Make sure you bring your formula sheet with you, just in case you, no, I don't remember if I put the formulas on the front or not. I think I did. But yeah, bring that with you for tomorrow, you're gonna want that, and a calculator. Okay, I'm down now to 2 loaner calculators. Okay, if you show up as the 3rd person without a calculator, I hope you're good at long division. Okay, because that's how it'll go. Make sure you have a calculator for tomorrow. My suggestion would also be that it is either, if you have a really new fancy one, fully charged, or if you have an older one, that it has fresh batteries in it. Okay, as that's pretty important. It's pretty awful if halfway through the test your calculator just quits. Okay, so please make sure that you've taken care of those little things to eliminate things that could cause you stress. Okay, I don't want you to be stressed. Those are 2 ways that you can eliminate some stress that are within your control, at least. Okay. So guys, it looks like we're pretty much on track. Okay. Our unit exam tomorrow. We're going to go over the unit exam on Thursday. We're going to start Unit 4 Thursday and continue it on Friday. When we come back from the break, we'll do some stuff about climate, like climate graphs analysis, and then we're going to move into global energy and systems. And yeah, before you know it, those 9 days that we have of class after Christmas, okay, will be done. All right, so make sure you come back ready to hit the ground rolling, running, whatever, okay, because it's gonna go quick, okay, after Christmas. All right. Okay, questions from you guys? Anything that we want to go over? I know I asked that at the beginning of class, but in case anyone was too shy at the beginning of class. Anything we want to go over from the unit?
I was wondering, I've been somewhat struggling when it comes to finding displacement on my velocity versus time graph.
Okay.
Just because I apparently make the wrong shapes and
Okay. I think I have one of those in the review package. Just let me get it open here. So the big thing with finding the displacement off of velocity versus time graph is that you're taking average velocity and multiplying by time. Average velocity is always going to be the height of a rectangle, or how much of the height of a triangle? Half, right? Because it's in a triangle, it's changing, right? The average would occur halfway through the change. Okay, so if we're looking at, okay, I don't know, you guys maybe did this one, Mr. Van Herf, but right, if we're looking at this one here, okay, during this first part, what's the object doing here?
it is accelerating.
It's accelerating, yeah, okay, and so that means its velocity is changing. Okay, so we would have, okay, this area that we want to calculate. Here's the other thing I saw quite a few people mess up on the quiz. The area is always between the line and what? And the x-axis. Don't get confused that the numbers are down here on the bottom of a Google Sheet graph. This is one of the things I don't like about Google Sheets. It puts the numbers on the bottom, not on the axis. Okay, the x-axis is wherever the y value is 0. Okay, so this is the area I want to calculate. For this one, it's this area that I want to calculate, not between the bottom. Okay, always make sure you are finding the x-axis and making sure the area is there. Okay, so for this one here, its height, I'm going to assume that's 4, okay, is -4, okay, and its base is 2. -4 times 2 is -8, divided by 2 is -4. All right, so this one's displacement for this part here, okay, would be -4 meters. It's also important that the negatives go in there, because after all, when we do this, we're finding the displacement, not the distance. We're taking average velocity and multiplying by time. Okay, for this one here, it goes from 2 to 5 seconds, so the base is 3. I'm going to assume the height is 6, 7, 8, I guess, we'll say, okay? So it's 8 high, it's 3 on the base, 3 times 8 is 24, divided by 2 is 12 meters, that's positive. Okay, for that one, then we got this box here. Travels at a constant velocity during that box, so its average velocity is 8, right? The height is 8, okay? The base is 2 seconds, so that'll be 16 meters, that'll be positive. And then for the last 2 seconds here, okay, it goes for, so 2 times 8 is 16, divided by 2 is positive 8 meters. That's all there is to it. The main mistakes I see people make is they're not using the x-axis. Okay, or here's the other mistake I see, has nothing to do with velocity versus time graphs. I see people do that on a position time graph. Okay, that's why we don't want to memorize things. On a position versus time graph, if I calculate the area of one of these triangles, I'm multiplying meters times seconds. What's a meter times a second? A meter second. I don't know what that measures. Okay, I don't know what a meter second measures. But on this graph, I'm not multiplying meters by seconds, I'm multiplying meters per second by seconds. And when I do that, I get meters. That is the units for displacement. Okay, so make sure you're calculating what you think you're calculating when you do something.
And I'm guessing to get distance, you just turn everything positive.
Then everything is positive, exactly, because distance is scalar. Okay, what else, guys? Anything else? Okay, obviously you heard in the recording yesterday, graphing is a big part of this unit exam. Okay, you're going to see a couple in the, or a couple or 3 in the multiple choice, and there's 1 of each in the written. Okay, 1 is linear, the other is irregular. Okay, so you'll have 1 that uses y equals mx plus b, and 1 that doesn't.
Can you go over the motion of each interval in the velocity versus time graph?
Okay, so right here, the object starts at -4, and this section finishes at 0. That means the object changes its velocity, right? Okay, what do we call a change in velocity? So in that part, it's accelerating, and it's accelerating in a positive direction. Is it moving in a positive direction during that part? No. No, its velocity is still in the negatives, still below the x-axis. Okay, that could definitely be a multiple choice kind of question. I give you a graph that looks just like that. Okay, is it doing the same thing here in terms of its acceleration? Yeah, it's accelerating in a positive direction. Not quite as fast. It doesn't look it's quite as steep. Okay, but it's still accelerating, or is it steeper? Steeper.
It's going faster. Or in the second part.
Here, it's going faster.
Yeah.
In 3 seconds, it changes to 8. Here, in 2 seconds, yeah. Okay, so it's accelerating faster in that part, okay? But in that part, it's moving forward.
So would we add the -4 or subtract it, like this 12, 16, and 8?
If I'm trying to find displacement, that's up to you. So what I would say, what I usually do if I'm doing the displacement on this, I go -4 plus 12 plus 16 plus 8. Mathematically the same to go all of those things added together -4.
Okay.
Mathematically works out the same. I just add them all together because I do vector addition. I teach that in physics 20, so that's the way I do it in my head. Yeah.
So then that straight part at the top is constant velocity, then the part that angles down, it's moving, like it's going slower, accelerating negatively, and then if the line kept going below the x-axis, would it still be going slower just backwards?
Nope,
Or-
it's accelerating negatively during this section. If the graph continued on down here like this, the rate of acceleration is still the same, but now it's actually going faster backwards. So this is strange because this looks like it's all the same, but what that would look like would be like if I strung a bungee cord across the room and I'm running forwards and I hit it. Okay, as I'm still moving forwards but slowing down, that's the part that's above the x-axis. I'm still moving forwards, but I'm accelerating backwards. And then I can't stretch it anymore. I stop for an instant. That's at the very end of the graph, right here. okay? Because right there, my velocity is 0 for an instant, and then I go backwards. The acceleration is the same the whole time. It's always negative whatever meters per second squared. But I actually start moving backwards after 9 seconds. Yeah? Okay. Oh, sorry, Ken, you have your hand first.
So for like the -4, you're starting backwards and then you change to go forward?
Yep. So this question starts out with me walking backwards slower and slower and slower, and then beginning to move forward. Yeah? Okay? Keith, your question?
Hey, so for one of the irregular graphs, I remember it flatlined at the beginning, was negative, and then flatlining, so it was moving at a constant velocity at the beginning. Do you have to
Okay.
find the area of that as well when you're trying to?
Yeah, if it's not on the x-axis when it's doing that, yes.
Okay.
If it's on the x-axis, the area would be 0, because there's no shape, right? It's always measured from the x-axis.
Oh,
Yeah.
makes sense.
If it flatlines on the x-axis, then stop. On a velocity time. Okay? Anything else there, guys? Okay, I would suggest going over that. I mean, we went over that quiz today, but those are good example questions to have a look at tonight when you're doing some practice. Yes, sir?
Can you go over the question 11 in the
Can I just borrow that for a second? Question 11. Okay. Right, so this is one of those ones like we did at the beginning of the unit, where we had like part 1 and part 2. Okay, I'm just going to write the givens down, and I'll give you your paper back. So first part, it averages 12 meters per second south. Meters per second south, covering 6,500 meters. Okay, and then 3,400 meters north for 8.5 minutes. Okay, so the 8.5 minutes is the trick here. I need it in seconds. Yeah, I need it in seconds. So I got to multiply that by 60 so that my units match the velocity I had over here. So 8.5 times 60, so I got a time of 510 seconds here. Okay, if I want to calculate, we wanted average velocity, right?
Yeah.
Okay, so if I want average velocity, I need the total displacement divided by the total time. Okay, so I have the displacement, I have the displacement. I can get the total displacement right now. This one is south, that one is north. So I don't want to add them, I want to subtract. Okay, so 3,400 or 6,500 minus 3,400 should be 2,100, right? I'm going to say that. I could be wrong. No, 3,100, not 2,100. Someone can double check my math. Okay, 3,100 meters south. Okay, and then I need the total time. I don't have the time for part 1. All right, so I've got to calculate that. T equals D over V. So 6,500 divided by 12.
Yeah, you're
That was right? Okay. Sometimes. Okay, 6,500 divided by 12. All right, so there's my total time, 541 for this part. Okay, so I take this time, I take that time, and I put them together. So we're looking at 1,051 seconds. Okay, with all the decimals on there. Divide those two things, and I've got my answer.
Okay, yeah, I think I just forgot to like put the time.
Yeah, that's usually the trick. Am I going to try a unit trick on you tomorrow?
Yeah.
I guarantee it. Yeah. Okay. Make sure you read the question carefully. Make sure all your units match. That could happen on anything. I could give you grams in an energy question. I could give you minutes or hours. Okay, and then meters per second in a question. Not that I would give you a question like this on your unit exam, but okay, with an acceleration question, something like that. What about vectors? How important are they? Especially important, okay, in all things, but I would say in acceleration in particular. Okay, how many people lost the mark on the acceleration quiz because they didn't put down the hill on their answer? Okay, like little things like that. Why lose that mark? Okay, just pay attention to the vectors, write them down in your givens, okay, so that you've got them. At the end of the question, you put the vector on if it's appropriate. Okay, little things like that. You hate to get nickel and dime, okay, on marks for things like that. Okay? Incidentally, I found out this weekend, useless trivia, where that expression comes from. Nickel and dime. In New York, way back when they were, I think it was like turn of the 20th century, so like 19 whatever. Woolworth, the guy who used to own Woolworth's department stores, was trying to get a loan to build like big tall buildings in downtown New York. The bank wouldn't give him the loans, so he had to go out and get other people to kind of co-sign for him to get the loan from the bank. He only needed it for one day. So he got this massive $1 million, several $1 million loan, okay, backed by all these other people for one day so that he could get this thing done. And then the next day he paid it back to the bank in nickels and dimes. He said, we're a dime store. At that time, Woolworths was a dime store, okay? And he said, I'm just trying to build this. And so he paid the bank back millions of dollars in nickels and dimes. That's where the expression comes from. Interesting stuff. Okay, we'll leave it at that today, guys. Remember, come in early if you want to start early tomorrow, okay?